Here we're looking at the ballistic pendulum. This is a question from a 1985 AP Physics exam. We're dealing with a bullet flying to the right. It's going to hit and stick to this hanging block, and then the bullet and block will first move to the right, and then will swing up to some new height. So we are looking for that speed v right after the collision, and we're working our way down to trying to find that maximum height that the system will swing to. To get through this problem, we're going to need concepts of both momentum to attack the collision and then energy to attack the swinging height change. As we attack the collision between bullet and block, conceptually we should review the conservation of momentum law, stating in the absence of external forces, the momentum before a collision will be equal to the momentum after a collision. Before the collision, we have a bullet flying to the right, the block is at rest. The only motion we have is along the x-axis or horizontal plane. Bullet will strike block and they will move to the right. So if there are any external forces, we would want them to act in this plane, left or right, horizontally. We don't have any of those, so because of the lack of external force, we expect momentum to be conserved. So here's an equation that's saying the same. Pi will be the initial momentum, that's for the moving bullet. Pf will be the final momentum after the collision, and this is the bullet and block added together because they are stuck together and moving as a unit. From our formula sheet, we observe that momentum is equal to the mass of the system multiplied by velocity. So I'm putting that in underneath each term. On the left, m lowercase b will be mass of bullet. Vi is the initial velocity of the bullet. The mass is added together because they're stuck together. I'll use capital B as the subscript for the block. And then V is what we're looking for. Here I'm just plugging in the known information. We were given the mass of each object as well as the initial velocity of the bullet. And now I have what I need to solve for that final velocity v, and I get an answer of 1.5 meters per second. Moving on to question B, we are looking for a ratio. We want to divide the initial kinetic energy of the moving bullet by the final kinetic energy of the bullet block system. So we'll be dividing Ki initial kinetic by Kf final kinetic. Although momentum is conserved in this scenario, I would not expect kinetic energy to be conserved. There are other energies when a collision happens. Specifically, heat is created, sound is created, you would hear it, so we won't have the same amount of kinetic energy before to after. From our formula sheet, kinetic energy is 1/2 mass velocity squared, so I'll plug that in the numerator. I want to use the mass of the bullet and the initial velocity of the bullet. This is the only moving object before the collision. After the collision, I again want to add the masses together of bullet and block, and now I want to use the velocity v that I solved for back as the answer to part A. Here I'm just establishing the given information. We know all four of these terms, and so plugging them in gets me a ratio of 665%. There is that much more energy before the collision than there was afterward. Lastly, let's attack question C. I'll add in a third picture as a visual. We are looking for the maximum vertical height above the initial rest position that is reached by the bullet block combination. So this red line will represent a visual for the height the block started at. You can see that after the bullet hit it, it has swung up to this new height. I'll call that h, and that's what we're solving for. What is the height of the system relative to where we started? Mentioned earlier, we'll need energy for this. I think changes of height are usually a good connection to energy. And the first thing we want to do with an energy problem is to establish our moments and try to track which energies are in our world. So the moments I'll use are this moment 2, if you will, right after the collision, and then we'll look at moment 3 when we reach the maximum height. Right after the collision, the only thing I see is a moving block and bullet system, so this system has a kinetic energy. And in the third picture, we've swung to this new height. We now have lost the kinetic because we're not moving anymore, but we do have a gravitational potential energy because of the new height. Well, I can't think of any other energies in this world or any external forces doing work, so these energies are equivalent. You can see that with the bar heights, and this equation will show that mathematically. Formula sheet tells me that gravitational potential energy is mgh, so I'll be subbing that in along with my kinetic energy formula. You can see mass on either side, so the mass will divide out, not a factor. Plugging in what we know, the velocity solved for back in part A, 1.5 meters per second, as that is the velocity here in the second moment, and we always know Earth's gravitational field strength. Performing the calculation gives me a height of 0.11 meter, and that will be the answer to question C. To summarize this one, the ballistic pendulum is a pretty commonly seen problem. Teachers like it because it combines the topics of momentum and energy into one. When you see a collision, you should be thinking about momentum, as usually energy is not conserved in a collision. When you see a change of height, you should be thinking about energy, as the height variable will not come up in a momentum analysis. If you found this video helpful, then I have other resources that you may be interested in as well. For more information, check out my website, shoot me an email, or follow me on X and Facebook. All of the links can be found in the video description.